Okay, in this video we're going to be discussing linear and angular speeds, but we say that what we really want to do is describe the motion of a particle traveling in a circular path. Okay, so for things that are traveling around, say the outside of a circle here, we say some point P. If we were to put this thing in motion, like start spinning it in this direction, the thing here is we want to try to describe the motion of this object. And so one way we can do this is we can actually say, well, in terms of speed, I thought speed is defined as being distance over time. So what we could say is, well, given this object that is some radius length from the middle of this center of this circular path, we could actually calculate how much distance it covers over time by really calculating its arc length over time. Okay, so we're going to go ahead and start by defining what we mean by linear speed. We say consider a particle moving at a constant speed along a circular arc of radius r. If s is the length of the arc traveled in time t, then the linear speed, we'll give this by the lowercase Greek or Roman letter v. We say of the particle is given by this. Linear speed velocity, or v, is given by just the arc length over time, or we define this as being s over t. So our linear velocity formula is however much distance you travel around the outside of this circular path over time. Okay. So let's go ahead and take a look at an example of where we might want to calculate this. It says the second hand of a clock is 8 centimeters long. Find the linear speed of the tip of this second hand as it passes around the clock face. And we want this measurement in centimeters per second. Okay, well, here's what I want to start with first. I actually want to start by drawing out this situation. So here's our circular path, and I'm actually going to start by saying, well, maybe our hand of this clock is facing this way. And so what I want to do is describe its linear velocity in centimeters per second. Well, here's what I'm going to need to answer for myself. I know it's going to need to be the arc length over time. And the thing is this, I don't know the arc length, but I certainly know that the arc length, and this just harkens back to our formula here, s equals r theta. We could actually find this just by saying we could take theta times the radius length of this clock. And as a matter of fact, the radius length of this clock seems to be 8 centimeters long. So we do know the radius, and then we would say, well, how fast is this thing traveling? Well, it didn't tell me about how fast it's traveling, but I do know this. I know it goes all the way around once in a single hour. So I suppose our time we could consider to be, an hour here. So let's go ahead and write this down. We say when time equals 1 hour, we will have spun around this clock 1 complete revolution. So we say, what would our angle be? Well, then our angle would have to be 2 pi radians. Okay, and you're going to go 2 pi radians every hour. And then also this, we would say that, not our time, sorry, but our radius length. We also want to record this here. We say our radius length in this case is 8 centimeters. So to go back to this formula we see up here, we could say, well, really all we need to do is say theta r, which is our arc length over time, and go ahead and fill in these values. So we say theta, 2 pi radians. We say 8 centimeters would go here, and we say this happens in 1 hour. Okay. So important here, we can go ahead and multiply this stuff straight across. We say 16 pi, I'm going to leave this written as a ratio, we say over 1 hour, 16 pi centimeters per hour. Now the thing is this, we did not want this in centimeters per hour, but we did want this in centimeters per second. So go ahead and put a box around this. Congratulations, you've already found your linear velocity. It's going this fast, but you're giving it to me in centimeters per hour. I'm giving it to myself in centimeters per hour. So what we need to do is we need to take this measurement, 16 pi centimeters in 1 hour, and we need to convert it into centimeters per second. So let's go ahead and start with this first conversion. We say I want to go from hours to seconds. And we say, well, what's the conversion from hours to seconds? How many seconds are in a single hour? Well, I know there are 3,600 seconds in a single hour here. So what we're going to do is we're going to put 1 hour on top. Let's do this. 1 hour on top. That'll get our hours to kick out here, and we say 1 hour is the same thing as 3,600 seconds. Okay, so now we've gotten our hours to kick out. We can multiply these straight across here, and we should be in centimeters per second. So I get 16 pi times 1 on top, so I get 16 pi, and on bottom I get 1 times 3,600, so I get this right here, and this is in centimeters per hour. Okay, so now we could certainly reduce this, but what we're doing is an application problem. So often what we like to do is just get a decimal. So we'd say really we can just take this 16 times our pi here and get this measurement. We say let's divide this by 3,600. We end up with 0.0139. It's not a very big number here. So our linear velocity is approximately 0.0139. And recall that we were measuring this in centimeters per second. Okay, and actually I need to go back and change this. I got stuck with hours there in my head. This is seconds. Okay, so that makes reasonable sense. It's not going very many centimeters per second, but we could actually determine that. So that is how we could use linear velocity there. We just say it's arc length over time. And you're typically going to have to draw out the picture here and talk about and think about the situation before you determine this. Now, another way we could describe the motion of this object, instead of telling me how much arc length or distance it covers over time, which is how we typically measure velocity, you could also tell me this: how many radians are you spinning over time? And we won't refer to this as linear velocity, but we would say how many radians I spin over time is what we're going to refer to as angular speed or angular velocity. So we say, moreover, theta is the angle and radian measurement corresponding to the arc length s. Then we say that the angular speed, and we give it with this lowercase Greek letter, it looks like a W. It's really just an omega is what it's called. It's the lowercase Greek letter omega, represents the angular speed of this particle. We just say it's equal to its radians over time, or angle over time. So I'll write that out here. We say that omega is equal to how much angle you covered in a set amount of time. Okay, so what I want to do is actually want to go down here and I want to try to give this a shot. Let's go ahead and try to describe the angular speed in radians per second of some circular blade here. It says the circular blade on a saw rotates at 2400 revolutions per minute. So one thing I'll point out here is this: if I'm going to find the angular speed, let's go and start with this. We need to find the angle over time. Angle over time. And the thing is this: when somebody gives it to you in revolutions per minute, they've kind of given you the time as 1 minute, but they didn't give you the angle. They told you how many revolutions you went. Now, the thing is, if we were to consider this as maybe our buzz saw over here and the blades spinning around and around and around and around and around, we say that 2400 revolutions, what would that be as a measurement of angle? And what I know is this: well, one complete revolution around, that would be 2 pi radians. So in general, what we could do is we could say this: if it's going 2400 revolutions per minute, let's write that out here. We have 2400 revolutions per 1 minute. I want to convert this into an angle. What I know is each revolution is 2 pi radians. So let's take this measurement right here and we'll just multiply it by 2 pi radians. Okay, and that should tell us how many radians we've rotated through in this single minute. And in this case, we get 2 pi times 2400 is 4800 pi, and this is going to be radians. Sorry to squeeze that in here. Radians in 1 minute. You must have gone this many radians in 1 minute. And I just want to say this really quickly here. If you want to know how big your angle is and it's given to you in revolutions, you really just take the number of revolutions times 2 pi in general. But now we know how many radians per minute we're going. So congratulations. Let's put a box around this. We just found the angular velocity. The angular velocity of this, I'll carry this over here. We say angular velocity is 4800 pi radians every single minute. Now the downside to this is we were not asked how many radians we went in a minute. We were asked how many it went per second. So what we're going to actually have to do is we're going to have to take this and convert it into seconds. But I know this, our conversion factor between minutes and seconds is this: 1 minute is 60 seconds. And we'll want to put the minutes on top here, because that'll get our units to cancel out. We say 60 seconds. So multiplying this straight across, actually we can reduce these values here. I actually want to do this. We say 60 and 4800. I noticed that they both end in a 0, so I could kick off one of their zeros. And 6 goes into 48 8 times, so 6 goes into 480 80 times, and 6 goes into itself once. So we really end up with this here. We say 80 times pi, radians on top, so our angular velocity is 80 pi radians, and this is all over 1 times 1, and we have seconds left over, so we say per 1 second. So here is our angular velocity in radians per second. We can certainly get a decimal for this, but what I want to do now is consider this. It says consider that the blade has a radius of 4 inches. So saying that this maybe represents our blade over here, we say that this thing is 4 inches. What I want to know now is this: find the linear speed of this blade tip in inches per second. Okay, so here's the good news. If I wanted to find the linear speed, we already know this formula. We say it's arc length over time. If I'm going to find arc length over time, I kind of need to know theta r over time, and I already know how many radians it spins per second. It's 80 radians per second. So our time is 1 second, and our angle measurement right here is going to be 80 pi of these radians every second. Now the only other question I need to answer is this: well, what's the radius length? And in this case we know that the radius length is 4 inches. Okay, so going ahead and multiplying this straight across, we get 320 pi, and this would be now in inches, and this would be per second. So there is our linear velocity, 320 pi inches every second. And actually, if we wanted to calculate that, that's quite a few inches. I mean, we could say 320 times pi. That's how many inches the tip of this part of the tip of this blade is going. And so about 1,005.3 inches every single second. Okay, but that's how you find or define and find both linear and angular velocity. It's either arc length over time, distance over time, or central angle over time, or radians over time. Cheers.